Ramanujan for G is now available on the Google Play Store. Try it out for free.
So we continue our discussion on um, with respect to waves. You know, um, so waves is, as we said, in some ways, we segue into waves from simple harmonic motion, right? We started that segue last time. Now we are segueing further into. We looked at the more complicated aspects of simple harmonic motion, and we promised that the concepts associated with things like resonance have broad implications also in uh, electricity and magnetism, or in electric circuits and in control systems. And so this is a very broad field, and we can only do so much justice. Students who want to learn more about this should consider maybe advanced studies in college, associated with this subject. So, having said that, we definitely want to move on um, to electromagnet to the next topic. You know, which is the idea that that we've been working on before, which deals with um, what happens with waves. Waves. Let me get started here. Okay, so waves happen when things move. Okay, so a wave can be thought of as a waveform in motion. Okay, so if you have a waveform, let's say you have a sine wave, right? And then that sine wave is moving, right? Now, a moving sine wave is what we know as we already discussed this a little bit. There are two types of waves: transverse waves. Let me share my screen. Let me share. Right, there are two types of waves. There is transverse waves, and then there is also, along with that, there is uh, you know um, okay, I hope you can see my screen. Yeah, okay. um, And so there is the transverse wave, and then there's the longitudinal wave. And when we discuss, so what is a wave? What is the mathematical description of a wave? How is v equals f lambda? You should definitely know that one. And how to use all this, you know. Later, we'll also look at E is equal to h mu around these frequency of electromagnetic waves, and all that. Okay, so this is the start of a long journey. You know, wave theory is the start of a long journey, and you must have figured it by now, right? So you have a sinusoidal wave, you have a transverse wave, and you have speed of waves on a string. Okay, and then there is speed of sound waves. Okay, so now first, the repeating and periodic disturbance that moves through a medium from one location to another carrying energy. So there's a disturbance that moves through a medium, right? And when we say medium, it could be like space. Okay, like for instance, light is a wave which goes through empty space. Okay, they do not represent transfer of particles from one place to another. They could, they do not necessarily represent. Okay, now they could involve some movement back and forth. Okay, wave disturbances travel from one place to another, and they're called progressive or traveling waves. Okay, now when they move, the wave moves. It's called a progressing wave or traveling wave. Extended wave disturbances which don't travel. Like, for instance, the string of a guitar, down, right? It keeps going in the same place, up and down, up and down. It's not like moving across space and time, right? So if you have y equals a square minus x square, say at t equals 0, you have a parabola, right? Now, if that parabola is now also you add a function of time, so you add at x equals x naught, right? At x it is at x naught, and then after that, or at t equals 0, it is at x naught, and then it is it then starts, the parabola moves. So this is at t equals 0, it is here, right? And therefore it goes from minus a to plus a is here, right? And so and then you have a square minus x square. So remember what you learned in what is that, function analysis, right? Function as x minus x naught. Now if it was moving through with time, it becomes a square minus x minus vt the whole square, right? And so then you have a square minus x plus vt as well. Similarly, the wave is traveling to the left, then you have a square minus x plus vt whole square. Okay, so a square minus x plus vt whole square, right? Or x plus vt less modulus is less than or equal to a, right? Y is a function of either. From the above example, one can deduce that any disturbance created given by f of x at time 0 will be given as a function of time, right? Now, a disturbance created as f of x at time t equals 0 will be changing, will be given a as a function of time, f of x comma t equals f of x minus vt comma t is equal to 0. Why? It travels to the right. F of x of t equals f of x plus vt, comma, t equals 0. T minus x over, where the wave is traveling along the positive x-axis, where the wave is traveling along the negative x-axis, it is t minus x over v. Okay, so the condition in which the wave equations are valid, the disturbance travels undistorted, the disturbance it travels with a constant speed v. Another way of looking at the wave travel is by considering the time interval between the wave's maxima traveling from origin to any point. So, how far does it go? Right? The wave has a set speed. Okay, and therefore you can say f of x comma t equals f of x equals 0 comma t minus x over v. Right? So let the time t be time taken be t, then t equals x over v. Therefore t minus x over v. Therefore, when the wave is traveling along the positive x-axis, t minus x over v, and the wave is traveling along the negative x-axis, going that way, t plus x over b, right? Therefore, the wave is moving. Now, if you look at the one-dimensional differential wave equation, it is given by dou square f x, dou square f by dou x square equals 1 by v square, dou square f by dou t square. Wave as an equation, or t plus xv, or t minus xv. The inverse of time period of the waves defined as frequency t equals 1 over f. Lambda v equals f lambda, and f equals 1 over t. Therefore, uh, therefore lambda equals vt, right? Lambda equals vt. Now, general form of a sinusoidal wave is a sine 2 pi times x over lambda plus minus ft plus phi. To generate such a wave on a string, keep one end fixed and the other end free, and oscillate the free end in a direction perpendicular to the string in a simple harmonic motion fashion as shown below. Right? So this is a sinusoidal wave, right? So sinusoidal wave is moving like that, right? So now notice that the f of x, right, with time, really the only thing that's you can think of this term, right, is what is changing, right? So at after a certain time, like what is really changing is the phase. Okay, so a sinusoidal wave, right, it starts like a maybe at t equals 0, it is a sine phi, right, or a sine 2 pi x plus phi, right, or a 2 pi x if you call it function of x, right? So so 2 pi x by lambda plus phi at t equals 0, then as you add a little bit, the the corresponding value changes. So at each t, it has a new the wave shifts, right? There's a phase change, right? So like that. Okay, so it keeps the wave is seemingly moving, but really if it is a standalone wave, it is moving in a simple harmonic fashion as shown below. Okay, so there's a phase change. So 2 pi by t, that's where it helps to learn simple harmonic motion before you learn this. Okay, so a sine 2 pi x minus lambda minus ft. So the wave, after some time, right, the wave has is still pretty much at t equals 0, right? It has a particular wave, right? At t equals 1, it has another wave, right? And so a sine x is what? Is an infinite, right? It is valid for all x, right? Sine x is for all x, right? So that's the thing. The phase keeps changing. It at any point, if you take a cut, it will go up and down, 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 right? So if you take at x equals 20, okay, then there it will go up and down, up and down, up and down, up and down, up and down. Okay, so now how fast does it go up and down, up and down, right? V equals f lambda, right? So in this equation, 2 pi x over lambda, right, plus minus ft, right? The coefficient of t is u. So if you write 2 pi by lambda equals, which is the like k, right, and plus, so you have kx minus omega t. Okay, so you 2 pi f is omega, right? 2 pi by lambda is called k. Okay, now these two, right, k and omega, right, kx minus omega t or kx plus omega t. Okay, so k and omega, the product of the two, right, or the division of the two is going to give you v equals f lambda. Okay, so that's the important thing. So omega by k is going to be the velocity of the wave. So you reduce it to this form, reduce it to this form, take the coefficient of t divided by the coefficient of x. So the omega over k will give you the velocity, right? So transverse waves, these waves have oscillations perpendicular to the direction of propagation. Longitudinal waves, these waves have oscillation in the same direction as the propagation. Okay, so that's the main thing. So in the case of sound, it's a longitudinal wave, right? The particles move like this. But in the case of, like, when you shake a rope or when you string up an instrument, the particles move in this direction. The wave moves in that direction. So if I do ta sa, right, the wave moves in this direction, but the particles, they move in a transverse, perpendicular to the wave. If they move in the same direction, then we say it's a longitudinal wave. Okay. Now, a speed of waves on a string, v is equal to square root of t over mu, where t is the tension, mu is the mass per unit length. So this you must know, right? So if you have a if you have like a stringed instrument, and then you do so, then how fast will the wave go? It is the proportional to the tension, square root of the tension divided by the mass, right? So if it's thicker, mass per unit length is higher, slower. So thick string, right? Now, faster, tighter, and thinner. If it's tighter and thinner, faster. T over mu. Square root of T over mu gives you the velocity. Okay, so now, uh, um, so when we use the net vertical force is given by that, right? So he's kind of trying to understand how to look at this, right? So T sine theta equals T times dy by dx, right? T sine theta equals T times dy by dx, right? T cos theta equals this, right? So you can then see that roughly T cos theta is equal to T, right? T sine theta equals T times dy by dx. Okay, so this is because it's a thin slope, right? So so a sine kx minus omega t, right? So the vertical force, so he's deriving this equation, right? So the vertical force on the section of the string, t times d square x by dt square times delta x, right? So Taylor's theorem is dy by dx equals dy by dx to 1 plus at this point plus the second derivative. What is the derivative of the second point? The derivative of the second point is the derivative of the first point plus delta x times the second derivative is y plus mx. Y equals y equals uh, right, mx m times x minus x naught. Y minus y1 equals m times x minus x, right? So at a second point, y, it will be y1 plus n times the difference. X minus x1 is delta x, right? So that's all Taylor's theorem really is, right? When he uses it here, right? So now the force is given by this t times d square x by dt square equals to this equals t times d square x by dt equals delta x. Therefore, the acceleration is given by d square y by dt square, right? Therefore, you find that it, when you cancel it out, you end up with, cancel out the delta x's, right? T times this equals mu times that, right? F is equal to ma, right? So because F is equal to ma, from that you can derive the equation, right? That, and you end up with T times K square equals mu times omega square, and as you know, K over omega over K is V. Omega over K is V. Therefore, T by mu equals V square. All right. Similarly, the speed of sound waves traveling a medium of bulk modulus b and density rho is given by v equals square root of b over rho. At high frequency, b is taken as the adiabatic bulk modulus, right? Therefore, v is equal to omega square by k square. V is equal to b over square root of b over rho, right? So that is the initial understanding that I want you to have. Okay. So with that, we are going to kind of move on. Okay, and look at the next set of ideas with respect to um, uh, this particular chapter. Okay, so the next set of ideas, um, so this is the basics of it. Okay, so how fast do the waves go, and then we look at the next set of ideas which deal with superposition and standing waves. Okay, now what is this principle of superposition? Okay, principle of superposition, so first let me stop. Okay. Okay, so the principle of superposition is going to help us um, understand what happens when you have a superposition of waves, and then we also look at when you have this tight string, and then you do that, it goes in and then comes back, goes, hits the wall, comes, bounces back, right? So in many ways, waves represent a certain kind of energy, the transfer or movement of energy. A wave is in fact energy, right? So if there are two or more coplanar waves arriving at the same point in space at the same time, the net displacement pressure is given by the sum of all the individual pressures. It's a very straightforward idea, right? So if you had many waves, at any point at each moment you just keep adding, right? So now if you keep adding, what is important here is that you still have this wave equation, right? Dou square f by dou x square equals 1 by v square dou square f by dou t square. See, this is the all-encompassing idea with respect to waves. Okay, this second derivative should equal 1 by v square times the time derivative, and you can see that when you do a sine kx minus omega t as well, right? Now, if you had many different additive sinusoidal waves, then you can see that this will very much apply. Okay, and so reflection of waves on a string tied to a rigid support, net displacement 0, net displacement equals sum of individual displacements, displacement due to incoming wave plus displacement due to reflected wave. Okay, apply this to an incident sinusoidal wave gives us incoming wave equals y equals a sine kx minus omega t. Y net at x equals 0 minus a sine omega t plus b sine omega t. Right? So then based on that, so at x equals 0, you can say b equals a, right? So the incoming wave and the reflected wave, they will have the same um, um, amplitude, right? B equals, right, incoming wave, the reflected wave, they have the same A and B. Okay, now reflected wave has the same argument. One is a sine omega t, the other is the sine kx minus omega t, the other is a sine kx plus omega t, because one is going this way, the other is coming that way. Okay, so see, the kx part gives you the wave at an instant of time with a phase shift. Okay, the omega t part reflects the movement. So there is a phase change of pi, the wave gets reflected from the rigid support. This is due to the fact that the argument of incident wave at x equals 0 is minus omega t, while that of the reflected wave is plus omega t. You visualize seeing there are two waves, one coming from the left, one coming from the right. So this is roughly all the material that I'm going to cover today. Let's look at standing waves. Standing wave is comes from the superposition of the incident and the reflected wave. So now you have an a sine kx minus omega t plus a sine kx plus omega t. You expand that, you find that the cos terms will drop out, so you will have only the sine terms, right? Therefore you'll have, it will add up on one side, the other term is going to drop off, so you have a constant times cos omega t. Okay, therefore you end up, notice that even though a wave equation is not of the form, right, this is due to the fact that y of x comma t does not represent a traveling wave, rather it's a stationary wave. Okay, so that's the point he's making, that it's not a traveling wave, it is a stationary wave, right? Standing waves are stationary, and so this is, it does not move, rather it's a stationary or standing wave, and can be visualized by saying that every point of the string oscillates up and down, but it does not move. You do this, what happens? Everything just goes up and down. So if you take a cut, what is a cut, right? Cut is, you'll just end up with a cosine t. So if you make x constant, you end up with a cosine t. Cos of t here, cosine wave, if you spread it out. Okay, so that's all there is with respect to this, and I'm now going to let's discuss the standing wave. We discussed that, right? Fixed on both ends, fixed on one end and free on the other, right? So we have two types of standing waves. One is the guitar one, right? You have two rims and then you do twang, right? And then you have this one, okay? Then the other one is this one, right? This is when you have this. You have this, like for instance, the flute, right? One end is closed, the other end you're blowing, right? Therefore, you have a one end fixed on one end and free on the other. Okay, and so closed pipe versus open pipe. Okay, so string fixed on two ends. Remember, V is root of T over mu, right? Therefore, V equals NV over 2L, right? Therefore, so the speed is NV over 2L. So there is a N over 2L times your original T over mu. Okay, so please keep that in mind. Root of T over mu times N over 2L. Okay, this is, so distance between nodes equals lambda by 2. Okay, so that's what happens in a standing wave. Okay, now string fixed on one end and free on the other, you have a plus 1 term. Instead of N over 2L, you have 2N plus 1 over 4L. Okay, and so that will give you um, your view. Okay, so so using that, what is mu? What is mu here, right? Mu is the frequency at which this vibrates. Okay, so we'll have many different frequencies, but they are all multiple. So n can only be integral. So 1 times root of T over mu by 2L, 2 times root of T over mu by 2L, because it can be one wave, two waves, three waves, four waves, five waves, because it has to be a integral number, right? So that's the important point. N over 2L times root of T over mu is the frequency. In this case, 2N plus 1 by 4L. So it is a one extra half. That one has many fulls. This has many fulls plus one half. So this is a 5.5 wave. This is a 5 wave or 4 wave, right? This will be 4.5, 5.5, 6.5 wave. So lambda n is 4L by 2n plus 1. Okay, so that's the frequency. Here, that's the wavelength. Okay, so remember that wavelength and frequency are product of the two gives you the velocity, right? But you must know what the wave lambda is. Lambda is 4L by 2n plus 1. This is velocity. Velocity divided by mu will give you V equals F lambda, right? So remember that. So what is V? Root of T over mu, right? And therefore, in this case, this n over 2L is going to be, or 2L over n is going to be lambda. In this case, 4L by 2n plus 1 is going to be lambda. So we'll have many different lambdas for each n, right? Correspondingly, we have the answer. So note these two equations. Okay? You can try learning more about it. Okay, so today I'm going to stop here, because we've been trying to figure out how all this is going to add up for us, and I don't want to go too far, too fast, so that it's not clear. Things are not clear. So I'm going to stop here and end today's class. All right. So with that, have a great weekend, and then we'll see you again next week.